Welcome to SpeakerLAB tutorial. This tutorial shows you the second part of Virtual Voice Coil software. It is referred to the new version, 2.2, and it will replace the version 2.1. In Virtual Voice Coil 2.2, a new feature is added. It is the calculus of non-uniform voice coil windings. Opening the layers configuration panel. Among the others configurations, it is now possible to select series non-uniform. For instance, we can choose 4 external layers. And selecting now the series non-uniform layers, it will be opened a new panel, showing a half section of the coil winding left side. We can save the simulation. But the software reminds us, it is necessary to save the project before. The displayed wire shape follows the selected wire section. Now we can recall the record number 1. Horizontal midline identifies the winding symmetry plane. It also represents the X offset coil position along the BX magnetic gap. It could be useful for an engineer to check if the midline is in the wire center or between 2 turns. Increasing resistance, the new rows are added to winding height. Virtual Voice Coil recalculates winding height in a continuous recursive process, giving priority to the DC resistance and fixing the outer diameter, OD, max. This method is mandatory for ensuring always the same position of the cut line inside the magnetic air gap. We can resize this panel in the smallest dimension. How we can see, in this case, the mouse pointer position has a different behavior inside the panel. When the mouse pointer is outside the voice coil area, mouse wheel acts as a vertical scroll bar, scrolling the window. When the mouse pointer is inside the voice coil area, the behavior is different, and we will see later how to use it. We can resize the panel, also maximizing it. On the bottom side, it is always specified the coil and direction. By closing this window, voice coil layers configuration is always reset to series. We are now using the default example of the Virtual Voice Coil trial version. As we can see, shifting the offset to 0.1 coil out, we obtain a mere total asymmetry of 0.21%. Indeed, the force factor and its mirror profile seem rather overlapped. Now, opening the layers configuration panel and selecting series non-uniform winding. Disabling some turns while keeping the mirror asymmetry graph under control. In order to reduce the amplitude and shifting offset to 0.03 mm coil in, we can see how the total asymmetries are now improved. And the XBL at BL minimum 82% is bigger of about 0.2 mm than before. One note about 0.03 mm offset shift. As we know, in some cases, this kind of precision represents a theoretical value for the loudspeakers manufacture field. Because, except for some kind of transducers, for example, tweeters compression drivers or microspeakers, mechanical tolerances are bigger, but for those cases, it is convenient to know what is the value to which to aim, or it is useful for selecting a setup or another. Now, we are going to design a cross-section of a 40 mm voice coil motor with a ferrite Y30 magnet, useful for 8-inch or a 10-inch woofer. Exporting the magnetic flux density and importing it in Virtual Voice Coil. Our woofer voice coil has a mean diameter of 40.68 mm, and the others dimension parameters are already set. We want a 8 layers voice coil. Selecting a copper wire with a section of 0.35 mm. Because our OD max must remain below 44.1 mm. Immediately, we can see magnetic flux has a strong asymmetry, and this is a typical case in which the loudspeaker motor could present high nonlinearities. Now, opening the non-uniform panel, it allows an automatic fine-tuning of the total turns number. Recalculating the DC resistance. It represents our starting point. It is possible to partially compensate magnetic flux density asymmetry, shifting the offset towards coil in. As we can see, we cannot reach to a good compromise, because red line of the rest position asymmetry is not constant along the ±x displacement, so the voice coil offset cannot completely compensate BL nonlinearities. In this case, we can decide to have a null of the symmetry point at max. We must accept asymmetries, and thus nonlinear distortions, inside the XBL range, and also along the residual displacement. Indeed, the XBL values in the two sides are very different, and the unique point where we have symmetry is only the peak displacement. But it is a very short range. Moreover, to reach this point the voice coil have to pass along all the asymmetries causing nonlinear distortions. Otherwise, shifting the offset, we can decide for a good symmetry at low membrane excursions. But in this case we have to limit the peak displacement to about ±6 mm, for not exceeding with distortions. We can save this simulation, if we want to restart or compare it. We can compensate these nonlinearities, working on disabling turns, into the non-uniform panel. Here, we are using the rest position asymmetry red line plot, as a guideline, trying to make it constant along the displacement. This is a respectable compromise. Now the rest position asymmetry is moderately constant. Moving the offset towards coil in of 1.31 mm, the total offset asymmetry is now 0.5%. We can save the simulation. Compared to the uniform voice coil, we have further reduced the maximum available excursion. But it is not a problem, because we have taken a cut line, smaller than the voice coil bottoming. When the mouse pointer is inside the voice coil area, mouse wheel shifts the active turns. Keyboard arrow keys are also accepted. It is very useful for finding the desired symmetry we are searching for, because all parameters, as well as asymmetry graphs, are always real-time updated. Now, evaluating our non-uniform voice coil, we can see there are some turns that could be difficult to realize for a supplier. So, we can try a different setup. Always searching for a constant rest position symmetry. Total offset asymmetry is now about 0.24%. And the voice coil has a more feasible implementation. Anyway, we want to check if it is possible to improve it. After trying different turns, this setup appears very interesting. But this is better. And this final release is about perfect. All asymmetries have a superior behavior. They are near to zero, and the rest position asymmetry is almost a constant line around the current offset position. As we have seen, asymmetry graphs offer very important information for designing good loudspeakers motors. The last note is related about the voice coil center of mass. When we have a uniform winding, the mean diameter of the voice coil winding coincides with its center of mass. The mean diameter, among the voice coil parameters, represents the geometrical center of the winding section, and it remains the same. But while turns are disabled in non-uniform windings, the voice coil center of mass will change in both horizontal and vertical planes. In this case, it is displayed the center of mass in the horizontal axis, and it is called mean diameter too. This last value is the new theoretical cut line diameter to use in magnetic fee for importing a new BX and fine-tuning the current simulation, if you want to increase accuracy at maximum level. Running the simulation, and then exporting magnetic flux density along the new cut line, and importing it in Virtual Voice Coil, updating the last simulation, with the cut line positioned along a smaller diameter, we can move a bit the offset towards coil in minus 1.7 mm, for improving symmetry, and then we can check if a further optimization is possible experimenting the non-uniform winding. Anyway, now comparing the uniform voice coil saved at number 1, with our latest non-uniform voice coil saved at number 7. As we can see, the offset asymmetry peak passed from about 23% to less than 1.3%. And the rest position is almost a constant line. And this will reduce greatly nonlinearities. Now, we are going to verify virtual voice coil result, compared to a finite element analysis with COMSOL multiphysics. Designing the same motor, in an axial symmetric 2D model, using the latest non-uniform winding profile. And shifting offset to 1.7 coil in. After running simulation, we obtain the displayed BL plot. Comparing to virtual voice coil, the BL profile and the BL value are about the same result. Don't forget you can toggle dark to light mode by simply clicking on the coil at bottom right. Anyway, the default color always remains dark, because all SpeakerLAB products, software datasheets and website are designed with particular colors, studied and selected to reduce power consumption in OLED displays. Thank you for watching.